Okay, just now we look at the application of the energy and force. And we are now in the ionic bonding. We stay at ionic bonding. So now we look at the arrangement of ionic, how they form in the three-dimensional. Okay, the rest you read. The rest you read. What is important is the way they pack. We call it a packing efficiency. Means the anion and cation, how they pack to each other. So they affected by relative size and charge neutrality. Size and charge. Okay. So for example, CSCl. So CS is positive, Cl is negative. So this is how they form based on their size and charge relatively. So again, packing is affected by these two factors, relative size and charge relatively. So you can see Cl is quite a big atoms surrounded by 4 atoms. So here you have 8 Cl atoms and 1 CS. Sorry, CS is at the center. Okay, CS is at the center. So you have 8 Cl and 1 center. Radius is given here. Radius of Cl is 1.8. CS is 0.16. NaCl. Cl. The NaCl also same. They have 6 plus center. It's based on how they pack. Of course, in the exam, we won't ask you to draw something like this. Right. So important is the packing efficiency. There's an equation where we take the ratio of positive to negative. So you take the positive radius divided by negative radius. Okay, positive at the above, negative below, you get 0.93. So this one is NaCl. Na is 0.95 divided by 0.181, you get 0.5. Okay. So as the ratio of cation to anion radius decrease, fewer anion can surround a cation, right? So as you can see here, same, both are Cl. But if your positive value, R positive value is decreasing, you see one is 0.169, one is 0.095. So when it decreases, it means fewer anion can surround a cation. Okay. Neutrality, second one, charge neutrality is by the electrical neutrality. Okay, so NaCl, one Na, there must be one Cl ion at the overall solid. So to form NaCl. But again, this one I won't ask in your assessment, just for your information. Okay. Now, LIF that we discussed previously, Li plus F. So this is what you draw during your secondary school, right? You use this one, Li plus this one. So again, ionic bonding is metal plus non-metal, metal plus non-metal. Okay. So structure of a lithium fluoride, it will look something like this. Okay. So in the test, later there's a calculation to calculate the form of this one. There's a calculation. Means later there's a calculation to calculate the length of all these things. Okay. So here we are at bonding first. So we are given some numbers. Heat of formation is negative. Heat of formation delta H. So this is just a step. This one you read. This one you read. Okay. So there's a formation, atomization. So it releases one electron outside, or ionization, right? So it releases heat. not release, is receive heat to release energy, receive, then it give away. Huh? Okay, the rest you read. So 5 steps. This one you read. So one's law is called Hess law. Hess law, you add all the formation energy together. Right? Hess law is the formation, you add all the energy of each steps. Okay. So they are formation of table or lattice energy. So this table, it give you lattice energy. Normally we will use the Joule column. Don't read the wrong one. This one, Kelvin, this one normally in the chemistry class, but for our module, we use Joule column. Melting temperature is this one. So lattice energy decrease when you move down in groups as the size of the ion increase. Right? So you move down the groups. So for example, you see the melting point temperature also increase. So you can see Li, Na, Li, Li. See the energy? Li, Na. So if you move down, the lattice energy decrease. The lattice energy decrease if you move down. Okay. So what I need to highlight here is all the value here is negative. Energy here is negative. So all value are negative here. Then lattice energy significant increase when ion involved in higher ionic charge. And so on. So this one you read. Temperature also. Ionic bonding. As it move down, you have a higher melting temperature. Means that the bonding is very, very strong. You want to break away, you need more energies. So ionic bonding, they are normally in mechanical properties, they are hard, they are rigid, and they are strong. Okay, so ionic bonding, you take metal plus non-metal, they are strong, they are hard, they are rigid. And sometimes, if they are too strong, they become brittle. Okay, they become brittle, like not diamond, but something like carbon and all this. Not carbon is another special example. Like for example, NaCl. NaCl is brittle, right? You hit it, then it become, you press it, then it break away. Ionic do not conduct electric. They are excellent insulator. So these are the properties for the ion. So all these properties, they are important when it comes to material selection. They ask you to select a certain material, why you use that one. So the first thing you go through is to explain if you are using ionic bonding kind of material, then all these are all these characteristics are important when it comes to material selection. Okay. So once it's melt or dissolved in water, ionic material can conduct electricity. 2, ionic diffusion. So ionic bonding or ionic solid, they are special. When they are solid, they are insulator. But when you melt them, you put in liquid, especially water, they can conduct electricity. For example, NaCl. You put NaCl, you put in water, you're able to conduct electric. Fracture mechanism is like this illustration of simplified diagram. For example, you take NaCl, sodium chloride. You have positive charge, negative charge, positive, negative charge in the Rubik form. So when you hit by a hammer, like in these two column here, these two column will move down. These two column will slide down, and you form a new crystal. Okay. So These slides here, what is important is that because you have positive negative charge, as you slide down, positive, they will repel the magnet. So it will make the thing more easier to break in the ionic bonding because of positive and negative charge. So when you slide out at a certain angle or certain degree, you meet positive, negative, positive, the thing will tear away because of ionic bonding. Okay. So the rest you read. We are done with the ionic bonding. Now we go to covalent bonding. Covalent bonding is that they share, this one is non-metals, means non-metal plus non-metal, you get covalent bonding, for example, carbon. Okay, C plus C, you get C squared, carbon molecule. Okay, covalent bonding is because small difference in their electron negativity mostly form metal, non-metal plus non-metals. So metals plus non-metal, you form ionic. Metal, non-metal, you form covalent. Okay. So covalent bonding, they share electron, and they form the covalent. So for example, hydrogen, one electron, they share it, they become covalent. There's no transfer of electron, you just share it. Okay, ionic, they will share, they will throw away or they will receive. This one, no, they share only. Okay, hydrogen. So once they share, they form a stable state. They form a stable state. Okay, so same, you have a graph of energy and forces. So this one is the energy. So this one is for hydrogen atoms. So again, you have a AO. AO is R plus R, big R. But this one, because of the same hydrogen, you take two hydrogen, you put them together. So there is a minimum energy there, which is become stable. There's an energy minimum, means the two molecules, they form covalent bonding, they are stable. So as you pull them away, your energy reduce, right? The energy will not reduce, it will increase. Negative become positive value, then flick off. Okay. So this is electron dot presentation. Lewis electron dot. This one you already know already. Okay. So to talk about covalent bonding, normally we will like to present with a Lewis electron dot diagram. For example, F plus F, you get one line. One line means a single covalent bond. Then oxygen, you share 4 electron, but you form 2 line here, it become double bond. Okay, so each line means 2 electron sharing. Two line means 4 electrons sharing. Okay, nitrogen also. Nitrogen, you have 3 lines. This is triple bond. Single bond, double bond, triple bond. Okay. Okay, so this one you know. Okay. This one, yeah lah. So the most you can have is to form a stable electron structure with its 8 electron outside. Means maximum is yeah, you can say it's 4 lines, but rarely, or you rarely get 4, because when they fall, normally it will go and share with other metals or non-metals. It will like more likely to form ionic bonding. Because it's like 4, you like in the middle, you are either receiving or let go. You're like not sure. But you have 2 hungry enemy. Like one side is hungry to throw away. One side is more hungry to steal 1 electron. So at the middle. So it depends on how strong is the other element. Right? So the rest you read, the rest you read. They also, and for the bonding attractive force, it depends on bonded atom, electron configuration, nuclear charges, and electron radius. So these are the 4 factors that we consider for covalent bonding. Okay. So as a material science, they discover that the bonding of electron do not stay in a fixed position between atoms. They will like a cloud. So this one will like run between here. You see a thick cloud there. Okay. So covalent bonding, they are directional, and the shape of the molecule not necessarily conveyed by the dot presentation. So they are directional. Okay. So this is a new table introduced to you. A new word called bond length. Bond length is the distance between the nuclear of 2 bonded atoms at the point of minimum energy. Mean when they're stable, where is the distance between the center of the molecule or atoms? So as you can see, single bond carbon is this one, 5.6, and so on. Now, what does this value means to you or important to you? This value is important to calculate the A0, A sub 0. A sub 0 is the distance between two atoms. Okay? And this one gives you the minimum energy. Okay, minimum energy. So what to observe here? Okay, higher bond order, bond length decrease. So for example, carbon, single bond, double bond, triple bond. The higher bond order, the bond length decrease. So here, the bond length means single bond, double bond, third bond, triple bond. So as you have high, the 2 atoms is attracted to each other because they sharing more and more electron. The bond length decrease, then the bond energy increase. Here you look at the carbon. So bond length decrease, the energy increase, bond energy increase. Okay. You explain through using the attractive force within the nucleus. Okay. So for example, carbon bromide, CBr, C plus Br, the first type, and second one, carbon iodine, Ci, and the third one is this one, CCl4, carbon chloride. So bond length increase as diameter of the atom bonding with the C increase. Okay, so this is how you read the things, bond increase. So this one you visualize either by periodic table or you refer to the this one. You go and read here. So bond length increase. So you have diameter of I larger than Br larger than the Cl. So this one diameter, because it's at more below, so you go below, so the diameter is bigger, right? So the greatest bond energy will be Cl. Okay, C and Cl will be the largest between C, Br, and Ci. Strength is another one. is like the bond energy. Okay, so the relationship is, this is the element, or you can say the mother and son. So if it's closest, then it's the strongest on the periodic table. Okay. So the lowest is C to Ci. You can see periodic table as a hierarchy. It's a like a hierarchy to the in the kingdom. So the highest one is a king and queen over here. Okay, the next one is a polar and non-polar. Polar and non-polar. So if the bonding electron is equal, then it becomes non-polar. Example, hydrogen, F2 nitrogen, they share the same number of electrons. They are non-polar. Okay. Polar is the sharing is unequal. So this one is called polar covalent bonding. So for example, hydrogen, they are called non-polar covalent bonding. For instance, the H and F, hydrogen fluoride, they are actually sharing unequal, this one, the electronegativity is different. It's different. Although there's one electron here, but the distance between the F and H is different. Okay, the distance F to the sharing phase and the hydrogen to the sharing space is different. So it become a polar, means there's a directional behavior. This one, okay, so for carbon, you already know how to write SPDF. So if a carbon here, you are at 2s, 1s square, 2s square, and this one is under P, 1 and 2, so 2p2 at level 2. Okay. Yeah, so be familiar with how you write the SPDF. Then you can bracket helium, and then helium is this one. So this helium. So you add this one, but normally we'll just write 1s square rather than helium for the top few element. Normally we'll write start to write the substitution after AR or nickel also can, if you're lazy to write. Okay. So here, so for carbon, you'll form two covalent bond with two half of the this one. So this, they will share this one. They will share this S and P, become two covalent bond, double bond. And sometimes carbon, they will form four covalent bonding, like what we discussed just now. You can see 4 line, but that one is hybridization. We do not go there. Okay. So this is how the hybridization happen. Okay. So ground states is at 1s, 2s, and 2p. What they do is that they split the 2s into p direction. Means they pull one of this over here. So the arrow in the S will be 1, and then P1, 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 so SP3. So we have four atoms to share. So you combine with another carbon, so you form 4 covalent, 4 bond. Okay. So ground state to hybridization. Huh? Okay, when it's a simplest form, if I can see this one. So in the simpler form, if for example, carbon, if you mix all the carbon atoms together, it's more easier to find carbon and carbon mixed together. It's like easier for them to become stable when they group with the same element. Okay, this one they explain. So what is the form of this? When the 2s here, you break one electron outside, the form of the carbon will change. You change to this one. sp3 is a tetrahedral covalent bonding, so it will change to something like that. Okay, it will change to this one. So that's why in the diamond, sometimes you see pyramid shape. The bonding change. The bond change. Bonding change. Okay. Hydrocarbon, and that one is important element because we are living in Malaysia. We produce lots of petroleum. So hydrocarbon is very important element for our country. So covalent bonding in hydrocarbon. So hydrocarbon, it means you have carbon and H, C and H. Right? You combine these two, it becomes hydrocarbon. Hydrocarbon, it means that the element you have H and C and different a different ratio of H and C give you different names. For example, methane, ethane, butane, ethylene, and acetylene. So don't worry, this one you will see, if this question come out, you will see there's a table to show you the configuration of element, and then the name also given there. Your job is to find the energy to break the bond, or how it changes from one shape to another shape, and so on. How polymerization happens, for example. Okay. So the simplest form is methane, CH4. It look like something like that lah. But I don't expect you to draw this one. No question will ask you to draw this one unless you are taking material science engineering or something. Then you need to draw this one. In our module, you don't need to draw this one. You need to know the formula for each one of these. Okay. So if you break this form, methane C with 4 hydrogen, and again, this is Bohr's models. Bohr's model. So if the question asks you to draw Bohr's model, this is you draw all the circle shape lah. So this is how you share, how you draw the Bohr's model. There are 2 electrons sharing here, then it becomes single bond. Same with either side. Right. Still, the fundamental covalent, you take non-metal plus non-metals. Ionic, you take metal plus non-metals. Another example for hydrogen carbon or hydrocarbon is benzene, C6H6. C6H6, it will form a ring with this one. So of course, we don't expect you to memorize this one. You will see this one also in the final exam. You will see this one. Means that you draw, you calculate. When you get the formation of C6H6, you can change this form into simplified symbol. Okay. So this is a straight line bonding notation. And this is a simplified of this one. So if you see there's a, let's say the question gives you this symbol plus some element inside, you need to change this one into this one. Okay. Means you go to the table behind the question paper. You see this one equal to this one. So you need to calculate this inside this one got how many carbon atom, how many hydrogen carbon you have, hydrogen you have, then plus the other side. So from there you calculate the formula of the form new material. And this one also. This one is the carbon-carbon with the ring. This one is called ring. So again, ring, once you saw ring, remember to go to the appendix behind the question, convert this one into C and H formula. Okay. So this one also have six carbon and 6 hydrogen. This one also have 6 carbon, 6 hydrogen. Both are same C6H6, but they have different presentation. One is this one, and this one is ring notation. Okay. So these are the material properties. Covalent, they are most gas molecule, liquid molecule, low melting solid molecule, and they are molecular, means they always come with a pair. And the bonds or molecule is weak. Example to memorize is carbon. Okay, carbon. And the next one is hydrocarbon, CH4, the most easiest example. Okay, then covalent bonding, some material called network covalent solid, something like that, right? So this one like diamond, right? Diamond, Si with the oxygen and so on. So we have completed ionic covalent. Now we go into metal bonding, also another main chapter for this module, because later we deal with metals and alloy. So metal bondings, they are found in metals and alloy. Alloy means addition of this one, the transition of metals and all this. So mainly they are from group, first group and second group, means 1A and second A element. So all these are metals. The most they have is 3 valence electron outside. The most is like, for example, here, sodium, some special material, right? So how you draw metal diagram? Metal diagram, because they have electron valence outside, they are always moving around. So you are very hard to capture them when you join metal and metal together. So you can only draw this schematic diagram. You draw positive charge with its ion core plus a sea of electron. Means the electron can transfer here and there. That's why metal, they are good conductor, good electric conductor. Okay. So for example, copper. Copper 29. So are you able to write the SPDF? So once you write the SPDF, you basically you know how many electron is outside the electron. So here, 29 copper, you have 12 electron packed around. Okay. How these 12 come into the picture? Later we will do a combination of Rubik's. So later we explain how you get 12. 12 neighbors. Okay. Okay. So this is what we see just now. So you have a sea of electron valence moving around. So this one you read lah. So you read. Okay. So this one also you read lah. So there's an attractive force between the positive core and negative electron form the cloud. So this one will give you metallic bonding. So all this you read lah. So this one is because of attractive force between the positive core and a negative electron cloud. The rest you read. Okay, the read. So melting point for metals is very high. Okay. So the rest, electron configuration, this one is your homework. You go and check whether correct or not. This one, electron configuration. Okay, and so on. So let's say I pull this column, row number 4. This one, A, Ca, Se, Ty is from this table. Right, 4s, 4s2, then 3d, you see Sc, this one. This one is inside. Here to here is 3d, not 4d. So that's why the energy for 3d is a bit higher compared to the 4d. Here they change, this one changed to 4d and then 4s and so on. Okay, so we pick one, Cu. Cu, you have 3d10 and then 4s1. So we check back again. Cu is here. Cu is at 3d. So you calculate from here 1, 2, 3, 4, 5, 6, 7, 8, 9. Then this one got 2s. Right. What is 10? 10. For S. Okay, you see copper, there's 4s, there's 1 electron jump to 4d. Okay, pure metal, all this you read, mechanical properties, they are more easier to form shape. The technical word is called malleable, soft and deformable. Right. So if you hit a hammer, so the whole orientation will deform. Okay, the whole orientation will deform. They call it slip. They just slip the orientation now. So excellent conductor, electric, heat, and so on. Okay, so we have done with the metallic. Another one is called mixed bonding. Mixed bonding means we take the main bonding, like for example, ionic covalent, metal covalent, and metallic ionic. There are 4 ionic covalent metallic. So they are mixed bonding. They mix between the ionic covalent and metal. They mix between 3. Okay. So don't confuse this one with the primary bonding. Only you mention this one if the question asks you how many mixed bond types in the primary bonding, then this 4 is the answer. So if the question asks you how many primary bonding you have, it's only 3. Okay. Metallic, ionic, and covalent. You only have 3 types of bonding, or metal-metal, non-metal, non-metal, metal, non-metal. So the rest you read. So there is if you have an ionic covalent misbonding, there's one new equation coming out. It is to calculate percentage of ionic characteristics by this equation. Percentage of ionic character 1 minus E. There is a symbol inside your calculator, small e. I use that one. E with the orange color in your calculator. Percentage of ionic characteristic or percentage of IC 1 minus E power 1 over 4 E X XA minus XB squared and whole thing times 100%. So the first thing, the calculating the ionic character means how many percent this one is under ionic. For example, if it is more ionic means it's more ion plus covalent kind of behavior. Okay, so XA, XB, they are electronegativity. So this one also you read from the table. Okay, there's a table or there's a chart for you to read these two numbers. Yeah, give you, and this one is called Pauling equation. So sometimes the question will help you. Based on understanding in Pauling equation, calculate the percentage of ionic character for this element. Okay. Okay, the rest is you read lah. Mixed bonding, semiconductor, GaSe. This one you read lah. Example. Okay, so these are the form of chemical that we are not usually seen, but we're already using it for most of your electronic devices, even in your computer. Nowadays, you have all this like this one. Now, how you calculate the Pauling equation? You will see this graph when in the exam. When you see this graph, means something to deal with Pauling equation. So, for example, we calculate the percentage of ionic character for GaSa and ZnSe. So this is the calculator, the formula, right? So you pull the Ga. So Ga here is what? Is 1.6, right? So how you read 1.6? Actually, you just read the numbers. So it's a three-dimensional chart. Electronegativity is the height of the bar here, right? And then this is the period, the family in the periodic table, family 1 until 7, and then the group here, right? So this is a group, and this is the row. Sorry, this is the row. So GaSa, they are same row, but different electronegativity. All right. So Ga is 1.6, As is 2. Just read from the graph there. Substitute inside here. So 1.6 minus something, 1.6 minus this one, but it's a square. So square, you still get a positive value. Multiply by, divide by 4, you get a negative value. E negative something. Then you minus 1, you multiply by 100, you get 4%. About there lah. Okay. So, and then the second question, you do the same. ZnSe, what is the Zn electronegativity? Are you able to find where is Zn? Zn value 1 Se. You notice that there are two Se there. One is here, one is here. Okay. Okay. So not sure, need to find out what is this. But we use the one on the right. Okay. Okay. So why do we use this one and not this one? Why? Because we are finding ionic phase. So if on the left, this one is metal, this one also metal, it become metallic configuration. So it's not that kind of question. Normally you are finding metal, non-metal, ionic. This one ionic so you know that it's metal plus non-metals. Yeah. Oh, sorry. C or C? C. It look like E to me. Okay. All right. But you substitute, you get 50%. Okay. Nothing complex here lah. So just summarize the rest you read lah. The rest you read about the electron transfer, all these things. Okay. So we are done with the primary, right? Later afternoon we continue with the secondary. Okay. Stop here.